Hello viewers, welcome back to this channel. So in this video, this is a continuation of Equilibria. Now in this continuation, we are going to be handling a topic of solvent extraction. So this video is presented to you by Yusuf, and you are advised to subscribe to the channel and you share it to your friends so that you can benefit as a family. So we shall start with defining what is called solvent extraction. So this is one of the applications of partition distribution, and we handled partition distribution under the previous video, which is labeled 005. So you're saying that solvent extraction, and you're saying that solvent extraction is going to involve, solvent extraction is a process that is going to involve separating one component from a mixture, and we are going to do that by shaking it with the extraction solvent in which the component is more soluble. So in other words, we are separating a component from a mixture, but in order to do that, we have to have a mixture of two solvents, but the other solvent we must introduce must dissolve the solid more than the other. So that's why we are saying that this involves separating one component from a mixture by shaking it with the extraction solvent in which the component is more soluble. So we are saying that each layer is then corrected and the solid can be obtained by distillation of the extracting solvent. So in other words, this has been a brief introduction about solvent extraction. Now the true definition of solvent extraction, after getting the background of it, we are going to define it as the partial removal of a solid from a solvent. Remember that this definition is going to be involving solvents, because we get two immiscible solvents, but the solid must be more soluble in either of one of the solvents that is present. So we are saying that solvent extraction is going to be the partial removal of a solid from a solvent, or its aqueous solution of a solid from a solvent or its aqueous solution by introducing another solvent. But this solvent that has been introduced must be immiscible with the first solvent, but it must dissolve the solid more. That's why we are saying that, but in which the solid is more soluble. So to easily remember and to easily memorize physical equilibria definitions, you have to understand them. So solvent extraction is simply we get two immiscible solvents, and then one solvent must contain that solid which is dissolved, and then we look for a way of removing that solid that's being dissolved in one solvent. And then the only way to do that is by introducing another solvent, but that solvent that has been introduced must be immiscible, and at the same time it must dissolve the salt that is present in the other solvent more. So that's why we are saying that it's going to be the partial removal of a solid from a solvent or its aqueous solution, probably by introducing a solvent, but that solvent must be immiscible with the first solvent that is containing the solid. But the solvent that has been introduced must be immiscible and it must dissolve our solid the more. Remember that we are not going to remove all the solid from the other solvent. That's why we are calling it a partial removal. So this is a key word when you're defining these statements, because you are not removing all the solid. So it's going to be a partial removal of a solid from a solvent or its aqueous solution by simply introducing another solvent, but that solvent that has been introduced must be immiscible with the first solvent, but it must dissolve our solid the more, or you can simply say, but in which the solid is more soluble. they all mean the same thing. So we are saying that the solid is commonly applied in purification of organic compounds present in aqueous solutions together with ionic impurities. And we say that organic compounds and nonpolar substances are extracted using organic solvents. And such examples include carbon tetrachloride, ether, or benzene. Now, what are the properties that must be contained by these solvents that we use to partially remove our solids? So this is the key, and this is highly examined to test your understanding of this topic. So I brought in a scenario. I was like, ether. Ether is usually preferred as an extracting solvent. Why? So these are the following solutions to such a question. Why could ether, or why could carbon tetrachloride or benzene be used as the extracting solvent? So Roman number 1, we are saying that reason being it is very volatile. Ether is a very volatile liquid and therefore can easily be distilled off. Roman number 2, ether is a good organic solvent. Whenever something is a good organic solvent, that means that it will easily dissolve, or also it will be more soluble in it. And remember, that's the aim of solvent extraction. Partial removal of a solid from one solvent by introducing another solvent, which is miscible with the first solvent but in which the solid is more soluble, or in which the solid dissolves more in there. So one of the components that you should not forget, first of all, we have looked at being very volatile, and the other one we have said that it should be a good organic solvent, and the other one is generally inert. If you look at carbon tetrachloride is an inert liquid. Let me hope you are briefed about that in your organic chemistry. So a good solvent must be generally inert. It shouldn't react. We say that thus it shouldn't react with any of the organic compounds present in that mixture. And lastly, so that is generally inert, good organic solvent and very volatile. And lastly, we are saying that it is miscible. It is immiscible with water. For anything to be separated, or for you to partially remove a solid from its solution or a solvent, it must be immiscible with the initial solvent in which a solid was dissolved. Now here we are saying that note, and what are we noting? We are saying that the extracting solvent, let me highlight this, the extracting solvent, we are saying that the extracting solvent should be used in several small portions. Now remember, I told you that for solvent extraction it's a partial removal. So how can we best remove our solid? This is the note explanation. So we are saying that the extraction of a solvent should be used in several small proportions. Why do we use it in several small proportions than being used all at once? So this is a very common question, and you should pay attention to this. I think let me bold it, because you are most likely not to miss it at any question that is involving solvent extraction. So why is it that we get more solid by using small portions of the extracting solvent than using it all at once? So the reason is because more solid can be extracted by using several small proportions of the extracting solvent than using it all at once. And we are going to look at that practically in the calculations. So calculations have started right away, and we are saying that examples. What are some of the examples that we are presented to be looked at? Now I always advise you to first pause the video and you take the notes so that you can understand later. And for those of you who already have the notes, it's advisable when you reach calculations, you take some of these questions and you try them out on your own and you see whether we shall get similar answers. Many students mess up this part, and it's what I want to explain properly. This is where you start making mistakes from when you are marking your scripts. So my number 1 or problem 1, we are saying that calculate the mass of an organic compound chew that can be extracted from 100 centimeters cubed of an aqueous solution containing 5 grams of chew. So this aqueous solution is initially containing 5 grams of chew, and we are going to use solvent extraction to remove. Remember, it's the partial removal. Solvent extraction can't remove all those 5 grams. So we are going to first use 100 all at once. 100 centimeters cubed of the extracting solvent all at once. And we are also going to use small proportions of the extracting solvent individually. So we are going to be using 50-50 twice to total up the 100 like in part A. So I want you to compare answers for the part A and answers for the part B. So we are saying that partition coefficient KD of chew between ether and water is 3. And I told you, for the organization of work, you always consider ether and water. That's your arrangement when you're presenting your KD values. So you're saying that solution, and what is this solution saying? In our solution, you're saying that let the mass of chew by 100 centimeters cubed of ether be x grams. So the mass, remember we're extracting chew, but we're not going to extract it all of it. We are going to extract portion of it. So the mass that we are going to extract be x grams. And we are using all the ether all at once. We had a total of 100, so we are using it all at once. So if the mass that is going to be extracted by ether is going to be x grams, then what will be the mass that is going to be left in the aqueous solution? So the mass of chew that is going to remain in the aqueous solution is going to be equal to the total ether which is initially present minus that one that we have extracted, so that you can get the remaining mass of ether of chew in the aqueous solution or the aqueous layer. So KD, as usual, KD is equal to molar concentration of chew as dissolved in ether to the molar concentration of chew as dissolved in water. So let's look at how calculations will be performed. Now, how do we get molar concentration? We get molar concentration by having the given mass divided by volume. So concentration is grams per volume. It can be in mass per volume. That's why we divide. So how shall we get the molar concentration of chew in ether? We get the given mass of ether, given mass of chew in ether. Remember that will be the mass that has to be extracted. So the given mass will be x, and then we divide it by the volume of the ether we are using, and we say that we are going to be using all the volume at once, which is 100. Now, how are we going to get the molar concentration of chew present in water? We get the mass that will be present after extraction. So after taking out portion of x, we shall remain with 5 minus x, as I explained here. So to get molar concentration, you get given mass divided by the given volume of water you are using. And our volume of water that we are using, we were given 100 centimeters cubed of aqueous solution. So the volume was 100. So that means that down here, this is enough concentration, and also up here that's molar concentration. Now in your O-level you studied finding reciprocal, so that will be x divided by 100, and also is divided by 5 minus x divided by 100. But when you find reciprocal, you find that 100 will cross. I skipped that step, but if you're not good in math, you try to show all those steps. Because in paper 1, if you skip steps, you are most likely to lose marks. So you find that after doing all that work, your side work, you come here. X divided by 5 minus x will be equal to 3. Now this is minus, it's not equal. So x, if you multiply 3 by 5, you get 15. And if you multiply 3 by x, you get 3x. Then you bring x on one side. You can take x this side. You can bring x this side. And that means that it will be 4x. 4x will be equal to 15. Then 15, if you divide 15 by 4, when you divide 15 by 4, you are going to get 3.75 grams as your answer. So this is the amount of ether that can be extracted when you use the whole volume of ether, which was given as 100 centimeters cubed of ether. So let's look at part B. And remember, in part B, we are looking at using that very volume but in small proportions. And our note above here say that when we extract using small portions of an extracting solvent, most solid is usually extracted. So we need to compare this value which we extracted using the whole volume with the values that we are going to be looking at using smaller volumes. So that's why we are saying part B, and we are saying that let the mass of chew that is being extracted in the first portion of the 50 centimeters cubed be x1. Now what will remain in the aqueous solution if you have extracted x1? So that means that our aqueous layer is going to remain with the mass of, you get the initial mass, which is 5, and then you subtract that one that has been extracted. So the remaining mass in the aqueous layer will be 5 minus x1. Now we will go back to the formula. Molar concentration in ether divided by molar concentration in water is equal to Kd, our partition coefficient, which is 0.3. Now what do you get here? When you do the math, we said that to get molar concentration of Cu in ether will be the mass that has been extracted in ether, which is x1, divided by the volume of ether to be used, which is 50. And when you divide mass divided by volume, this is the same as molar concentration. So you have to pay attention to that. So grams divided by 50, the mass which was extracted was x1 divided by 50. That's molar concentration of Cu in ether, divided by molar concentration of the remaining Cu in water or the aqueous layer. Is going to be the mass left, and we get the mass left by getting the initial, which was 5. We less our extracted mass, and then we divide it by a given volume of water that we are using. And the volume of water we are using, we are told in the question to use 100 centimeters cubed of water. Now if you do the math, I say that if you find these steps so confusing, you put it aside. You say that x1 divide by 50, then divide by 5 minus x1, divide by 100. Then you find reciprocal. When you find reciprocal, 100 goes up here, and 5 minus x goes down here. Then this 50 crosses that 100, and you get 2. And 2 multiply x1, that's why you have 2x1 here. And then this 5 minus x is going to remain in the numerator. So that's how you simplify that calculation. And it's very important to show that step or working during paper 1, because paper 1 you are marked each and every step. People who miss out marks in paper 1, they are not presenting each and every step required. So let's proceed. Let me first clean up this sheet. So when you do that math, you'll find that you remain with 2x1. You remain with 2x1 divided by 5 minus x1. Now if you cross multiply, this 5 will multiply, this 3 will multiply this 5, and then you get 15. And this 3 will also multiply x1. Then you get minus, this is minus, not an equal sign, minus 3x1. Now if you take this one this side, you end up with 5x1 will be equal to 15. And if you divide through by 5, your x1 is going to be equal to 3 grams. Now pay attention that this is the mass that can be extracted using the first 50 centimeters tube portion of ether. So don't forget that. Now let's proceed and we see. Now we have extracted, remember you have to follow up. We have extracted 3 grams. Now that means that how many grams are remaining in the aqueous layer? Because we need to do the other extraction in the second round using another 50 centimeters tube of ether, so that we total up that one which was present in section A, which was 100. So we have so far extracted 3 grams. So what is the remaining mass in our aqueous layer? Because that's the mass that is going to be our initial that we need to extract from again in the aqueous layer. So that's why we are saying that after extraction with the first portion, the mass that's going to be remaining in the aqueous layer is going to be, this was supposed to be 5 minus 3, so interchange these letters in your notes, because 5 was the initial and we have so far extracted 3. So what is going to be the remaining mass? The remaining mass, you find that it's going to be 2 grams. And we are saying that let the mass of Q that is going to be extracted in our second extraction of 50 centimeters tube portion of ether be x2 grams. So if mass of that mass to be extracted is x2, what mass is going to be left in our aqueous layer? Remember that in our aqueous layer we have 2 grams to extract from. That means that in our aqueous layer we are going to remain with 2 minus the mass we extracted before, which is x2, just like we have been explaining. So you repeat your expression. Now it's better to write the formula, though in my work I didn't repeat the formula, but in mark substitution in your papers you should always present it. So it's going to be molar mass of ether, molar mass of Q in ether, divided by molar mass of Q in water, will be equal to our Kd. Always remember that Kd is always going to remain constant. So to get molar mass, we get grams divided by volume that we are using for that extracting solvent. And we do the same thing to water. Mass left was 2 minus 8 divided by the total volume of it that we are using to get molar concentration. If you do the math, you find reciprocal and you cross out everything, you end up with 2x2 divided by 2 minus x2. And if you cross multiply, 2x2 is going to be equal to 6, because 3 will multiply 2. 3 will multiply 2, you get 6. And then 3 will multiply x2, you get negative 3x2. That's after cross multiplication. And then if you correct subjects, you take this negative 3 the other side, it's going to be plus, and you have 5x2, which will be equal to 6. Now if you divide through, the second mass that you are going to extract is going to be 1.2 grams of Q. So that means that in the first portion, remember in section A, we got around 3.7. But here we used successive volumes of the extracting solvent. We didn't use it at once. We used 50-50 to add up to the 100 that we used in part A. And here in the first extraction, we got 3 grams. And in the second extraction, we have got 1.2 grams. So what will be the total mass that has been successfully extracted? Total mass that has been successfully extracted is going to be got by adding x1 plus x2. So you have 3 plus 1.2, and the final answer is going to be 4.2. So usually when you set those questions, we ask you to state or to comment on your answer. You compare both section A answers and section B answers. So usually the comment is going to be, there is a higher mass of Q that is being extracted on using successive small portions of the extracting solvent compared to using the whole solvent at once. So let's look at that in the next slide. So this is example 2, and in this example we are going to be looking at some of the other numbers. So you are being told to calculate the percentage by mass. Remember that total percentage is always 100 of iodine that can be extracted using 100 centimeters cubed of water. Remember that for the aqueous layer, its volume is always constant. You wait for the extracting solvent's volume to be dictated, which is always dictated in the question. So part A, we are using the whole volume, and part B, we are using successive small portions of the extracting solvent. And in this time, our extracting solvent was benzene. And we are saying that the partition coefficient of iodine between benzene and water is 5. And always remember that this one always remains constant. So we are saying that let the percentage by mass of iodine that will be extracted by 100 centimeters cubed of the extracting solvent, which is benzene, be y%. And I told you that means that the aqueous solution or the aqueous layer or our solvent, in this case our solvent was water. Since the total percentage is 100, that means that it's going to be 100. So the percentage by mass of iodine that will be remaining in the aqueous solution will be the total percentage minus that one that has been extracted, which is y. So repeat the same procedure as I've been explaining. This arrangement of molar concentration of iodine in benzene to molar concentration of iodine in water is good from this statement, because they say that Kd between, they brought benzene first and then water next. That's the arrangement you should also follow. So proceeding, Kd will be equal to molar concentration of iodine as dissolved in benzene to the molar concentration of iodine as dissolved in water. And our Kd has been given as 5. To get molar concentration, I said you get given mass, which is y, divided by total. And here we are, part A, we are using the whole of it, which is 100. So that's how we get molar concentration, given mass divided by volume. And then for water, molar concentration of iodine in water, you get mass of iodine left in water, which we already got as 100. So we usually get that mass by getting the total mass, which was 100, since it was given percentage, and we less that one that was extracted. So that's why we have 100 minus y. Then we divide by the volume. The volume of the aqueous solution or the solvent will be dictated in the question. So here it was dictated as 100 centimeters cubed of water, which will be equal to 5. So if you do the math, you remain with y divided by 100 minus y, and this will be equal to 5. Then if you cross multiply, 5 will multiply 100, and also 5 will multiply y, and then you have y will be equal to 500 minus 5y. If you bring 5y this side, you get 6y to be equal to 500, and you divide through by 6. When you divide through by 6, you remain with y being equal to 83.33%. So this is the percentage you get, percentage that can be extracted when you use the whole volume of the extracting solvent at once. So what happens when you just use portion of it? Like in part 2, they said we use two successive portions of 50 centimeters. Say that when you add up those 50, we can get up to 100, like in part A. So first of all, you have to dictate the percentage by mass to be extracted in your X1. So since we let the percentage of iodine to be extracted in the first 50 centimeters cubed of the portion be X1, so what will be the mass left in the aqueous solution or in water? It will be the initial. Since this is X1, the initial was 100. It will be 100 minus X. So to get molar concentration of iodine as dissolved in benzene, it will be X1. I say that always repeat this formula whenever you start your calculations because it will help you. You always repeat this formula here because some examiners are very sensitive. They usually mark substitutions. So molar concentration of iodine given mass divided by volume, and molar concentration of iodine in water, it will be the left mass, which will be 100 minus x1. This x1 is the mass that was extracted. So to be extracted, that means that we shall remain the mass of that component we shall remain with will be 100 minus x1, and then you divide it by 100 is equal to 5. I told you how to do this. You put it in your side work first, and then you can understand what you're going to end up with. Usually we end up with 2x1 minus divide by 100 minus x1. After that you cross multiply. If you cross multiply these two, you remain with 2x1. 5 will multiply 100 to give you 500, and 5 will multiply negative x1 to give you negative 5x1. So you bring this negative 5x1, you bring it this side, and when you bring it this side, it turns from a negative to positive. So that's why it becomes 2 plus 5x1, you get 7x1, and it's going to be equal to 500. So what will be x1? You divide through by 7. When you divide through by 7, you're going to get 71.43 as the total mass that was extracted in the first extraction. So this is the mass that we extracted in the first extraction. So what's going to be the mass that is going to be left in the aqueous layer? So to get the mass that will, because that's the mass that we are going to extract on in the second extraction. So to get the remaining mass, you're going to get the total percentage, 100 minus 71.43. So let's look at that in the next slide. We are saying that thus the percentage by mass of iodine remaining in the aqueous layer, remember that we have so far extracted 71.43. So what is going to be remaining in the aqueous layer, because that's what we are going to begin on our second extraction. So we get the total mass, which is 100, and then we less what you have extracted, which is 71.43, and then that means that the aqueous layer that we are going to extract in the second time only contains a total of 28.57 of iodine that we are supposed to extract. So let the percentage by mass of the iodine extracted in the second successive portion be x2. So if this one is x2 that has been extracted, then what will be remaining in that aqueous solution? We shall get this total, this initial total, and we less that x2. So that's why you're saying that molar concentration of molar concentration of iodine in ether or in benzene is going to be equal to x2, which is the given mass, divided by 50, which is the volume that we're using, because we say that we are going to be using small proportions of 50. So that's how we get concentration. Always is mass divided by volume. And then the mass that will be left in the mass of iodine that will be left in the aqueous solution will be what? Will be the total which we left after the first extraction, which is 28.57, and then we less x2, which is the mass that has been extracted in the first position. Then to get concentration, you always get the mass divided by volume. Whereas the volume of the aqueous solution that we use is always constant, which is according to what the question gives you. In my case, it was 100. And also KD is always constant, partition coefficient. And the question gave us 5. Now you first do the math, and then you end up with this. I gave you a side work of how you can do that math to end up with this. You first calculate this out on your own so that you don't make mistakes. And you should include that step if you don't want to put your answers at risk or to avoid missing out some marks. So 2x2 divided by 28.57 minus x2. The next thing here is to cross multiply. On cross multiplying, you have 2x2 being equal to 5 multiplying these brackets. So you open up these brackets, 5 multiplying 28.57. Now I skip those steps because my space was not enough, but you're not supposed to skip them. So it will be 5 times 28.57 and also 5 times x2. Now this will be negative 5x2. Then you bring negative 5x to this side. It will become 7x2. After that you divide it and you end up with your answer being 20.42. So this is the mass that we extract in the second extraction. So what will be the total mass that we extract when you have used half of the proportions of the extracting solvent individually? So we shall get total mass. Total mass of iodine extracted in the two successive portions is going to be equal to our x1, which is 71.43. You add our x2, which is 20.41. And then you end up with a total of 91.84%. So let me hope that has been very clear to you. Now number 3, you are advised first pause the video and you try it out on your own. So number 3 is saying 50 centimeters cubed of a solution contains 0.966 grams of iodine that are dissolved in tetrachloromethane, was shaken with 50 centimeters cubed of water. Now we are saying that calculate the amount of iodine that remained in tetrachloromethane. And we are saying that the partition coefficient KD for iodine between carbon tetrachloride and water will be equal to 85.25. And then Roman number 2, they have prompted us to explain your answer in Roman number 1, how your answer in Roman number 1 would be affected if the iodine solution we are using in tetrachloromethane was shaken with aqueous potassium iodide. Now this is knowledge about your group 7. What do we talk about iodine in group 7 with issues concerning potassium iodide? So you should always be able to interlink the chemistry. So let's look at the approach for this question. So you're saying that you're going to say that the mass of iodine extracted by the 50 centimeters cubed of water be 8 grams. So what's going to be our remaining mass in the organic layer, which is carbon tetrachloride? So the mass remaining after extraction will be the total or the initial, which is 0.966 minus you less the A in grams. So KD is always equal to molar concentration of iodine as dissolved in carbon tetrachloride. Now I want you to realize that carbon tetrachloride must be subscript. You shouldn't write it on the same line with the molar concentration brackets. So it will be, and same applies to water. So KD, or partition coefficient, is given by molar concentration of iodine as dissolved in carbon tetrachloride divided by molar concentration of iodine as dissolved in water is equal to 85.25. Now I told you that this arrangement is always stated in the bracket when they are giving you this constant. the order they put them in is the order you are supposed to use. How do you get molar concentration? We get molar concentration by dividing mass that has been given by the available volume that you are using. So that's why we are saying this is going to be 0.966 U.A.C.E divided by 50, as you have explained here. Then divided by A divided by 50. So if you do the math that I told you earlier on, you end up with 0.966 less A divided by A is equal to our KD, which is 85.25. And you end up with 0.9. If you cross multiply, you end up with 0.966 minus A is equal to 85.25A. But then you bring that A this side and it will add. That's why you're having 86.25. So let me hope you're not confused there. So when you divide, you end up with your A being equal to 0.0112 grams. So that means that amount of iodine remaining in the organic layer is going to be this, which is substituted here, 0.966 you less 0.0112, and your final answer will be equal to 0.9548 grams. So let's look at the explanation of Roman number 2. We say that the mass of iodine remaining in the tetrachloromethane layer is going to greatly reduce. Why is it reducing? Why did we say in group 7? Group 7 is a video that has been uploaded on this channel too. We say that the iodide ions from potassium iodide from potassium iodide solution are going to combine with the iodine to form a soluble complex. So we are going to study a topic known as chemical equilibria, and we are going to look at this in details. So the iodide ions from potassium iodide usually combine with iodine to form a soluble complex. So that's why we are giving this equation: iodine in aqueous combining with the iodide ions from potassium iodide is a reversible reaction. That's why we are going to look at it in chemical equilibria. They usually form triiodide ions, which is potassium triiodide, which is always a complex that is soluble. So what will be the effect of that? We are saying that this is going to greatly reduce. This reduces the concentration of iodine in the aqueous layer, and thus for equilibrium to be established, more iodine moves from the organic layer to the aqueous layer. But we are going to look at this more in details in chemical equilibrium, which will be a topic also started in this playlist of physical equilibrium. So this is a sample question. It can be brought in paper 1 just to test your understanding, and we are saying that it's about data interpretation. So you're advised to finish it up. I think I didn't finish all of it, and you can consider it as your assignment. So pause the video, you take the notes, then the question, and then you try it out. I helped you with some part of it. This is what you need to do, and then you proceed with your calculations. After that, you take the number for marking or for verification by your teacher. So write the number and try it out. This video, we are also introducing a new application of partition coefficients, but we are just introducing it, and I want you to read through these notes before we come in for it, because the calculations for it are somehow serious and they require you to have hard knowledge about it. So that's why I decided to make it a continuation of this video, so that you can take the notes for it You go through them and you try to relate with the topic about what's coming in the next video. And that will be our last video about physical equilibria on this channel. So investigation of complex ions. Now we are saying that many ions undergo complexation, like you have looked at in your O-level practicals. And we are saying that when a ligand substance is added to their aqueous solution, so we are saying that the formula of the formed complex, and hence the number of the ligands and molecules or atoms that are connected to the central metal atom in a complex ion. So be aware of that. Hence the number of ligand molecules coordinated to the central metal ion can be determined by the application of the partition law or the distribution law. And we are saying that you consider the reaction between copper 2 ions and ammonia. In the first rub of this. So when you are reacting copper 2 ions with n moles of ammonia in aqueous, you are going to get a complex which is in this form. So the main emphasis of this topic is to find this value of n here. And how are we going to find it? So we are saying that determining the number of moles of N of ammonia that are combining with 1 mole of copper 2 ions cannot be done by direct titration, because the acid will react with ammonia in the complex as well as free ammonia. So we are going to be looking at all this in the calculation, and you are going to understand it in details. But before that video is uploaded, you are advised to first understand the notes about it. We are saying that we are going to be looking at how we are going to find that N, but we are saying that it can't be got by direct titration, because the acid is going to react with ammonia in the complex and as well with ammonia that has been left free. Remember, when you are forming a complex, these copper ions are going to be less. We add ammonia in excess. Let me hope you are getting me. So when these ones are less, you find that the less ions react with less ammonia to form a complex. So that means that copper ions are all going to be taken away. But since we added excess ammonia, more of the ammonia molecules are going to remain free. So that's why we are saying that the acid is going to react with this one, and also it's going to react with the complex that's being formed. And that's the good explanation for this paragraph. So proceeding, we are saying that however, when an organic solvent is added to the aqueous solution, the complex ion formed cannot dissolve in the organic solvent. So we shall be introducing, and this is about distribution law. When you introduce another organic solvent to this solution having this complex, we are hindering the reaction between the complex and the acid. So that's why we are proceeding, as we are saying that only the free ammonia molecules will be partitioned between the aqueous layer and the organic layer. Therefore, the total concentration of ammonia in the aqueous layer consists of the complex ammonia and the free ammonia. Like I explained, we add excess ammonia. There's ammonia that's going to be used to form a complex, and there's that one that will be left free. That's why we are saying that the total concentration of ammonia in the aqueous layer is going to consist of the one that is being complexed and the one that has been left free. So we are going to be looking at that. So in this video, we are going to look at a simple experiment, and in this simple experiment, we are going to be looking at how we can determine the formula of a complex being formed between copper 2 ions and ammonia. But usually the emphasis on finding this value of N. So pay attention to these notes and make sure that you read this experiment and you understand it before watching the next video, that will be 007, that will be uploaded still on this channel. You are advised to share the channel to your friends so that you can benefit as a family. So you are saying that excess aqueous ammonia is added to a solution of copper to sulfate of a known concentration that are present in a separating funnel. And after that, we add an organic solution. That's why you're saying that an equal volume of trichloromethane is going to be added to the solution in the separating funnel. And the mixture, first of all, it's stoppered. When you put this mixture in the separating funnel, you stopper the separating funnel. I missed it in this paragraph. The mixture is stoppered, the flask is stoppered, or the funnel is stoppered, and the mixture is shaken. Because you can't shake the separating funnel when you have not stoppered it. Stoppered it is like closing. The mixture is shaken and allowed to settle at a constant temperature for equilibrium to be established, as also the layers separate. Now we are saying that the layers are then removed. Layers are removed from the funnel and the known volume of the organic layer is pipetted and titrated against standard hydrochloric acid. Whenever you are using a standard solution of an acid, we always use methyl orange indicator, like I explained before in the previous video, to determine the concentration of ammonia in the organic layer. So Roman number 3, from the known value of the partition coefficient, we shall always give you this value in your calculations. From the known value of the partition coefficient of ammonia between water and trichloromethane, the concentration of free ammonia in the aqueous layer is going to be obtained from this expression. So we are saying that the Kd that has been given is going to be equal to molar concentration of ammonia that is free in the aqueous layer divided by the molar concentration of ammonia that is dissolved in the organic layer. So you need to pay attention to that. So I'm proceeding. Saying that a fixed volume. I'm proceeding and saying that a fixed volume of the aqueous layer is also pipetted and titrated with a standard solution of hydrochloric acid. And whenever we use hydrochloric acid or a standard acid, we always use the indicators methyl orange. And this is going to give us the total concentration of both the complex and uncomplexed ammonia present in the aqueous solution or in the aqueous layer. But you are going to be more of aqueous layer. So you are saying that the concentration of ammonia complexed in the aqueous layer is going to be obtained from these expressions. So this is molar concentration of ammonia complexed. This word complex must be a subscript. Is equal to molar concentration of ammonia present in total in the aqueous layer. You less molar concentration of ammonia that is being free in the aqueous layer. But notice that these words are subscripts. I wasn't able to do that. Maybe I was panicking. So you're saying that the number of molecules of ammonia that are going to be combining with copper 2 ions to form a complex is going to be obtained from the following formula. That is expressed as the ratio of the concentration of the complex ammonia to that of the copper 2 ions. But remember, these are just formulas, and I'm going to show you step by step on how to calculate, to make these calculations using calculations, and it's going to be super easy. You can read through that experiment so that you can get a good background before you go to the next video. This video has been presented to you by Uace Yusuf, and you're advised to share the video to your friends who are also in need of success. So for those of you having your papers, I wish you success, and you thank God for having this opportunity to access such resources. And for those of you who have inquiries or who want books, you can reach me out on the following numbers. So we meet again in the next video.